Deep inside your computer, at the physical level, there are no text documents, no video game characters, and no bank balances. Instead, there is only a vast physical landscape of billions of transistors, each holding microscopic electrical charges. If we isolate a sequence of 32 bits sitting in this memory, it contains absolutely no intrinsic meaning. It is merely a physical state of on and off switches. Look at this 32-bit sequence. Read with a signed integer protocol, it calculates a whole number, 1,096,000,000. Apply a floating point protocol, and the same states become the decimal 14.0. Apply a UTF-8 protocol, and they become text. Look at this stone tablet. The Greek text at the bottom provided the semantic bridge necessary to translate the hieroglyphs at the top. Data representation works on the same principle. Without a shared system of interpretation, the underlying binary remains purely an electrical state. To truly understand computer architecture, we must strip away the illusion of software variables. We have to track exactly how hardware mathematically encodes, physically transports, and caches these electrical states. The hardware faces a severe physical constraint. It must represent infinite fractions and negative numbers, but it only has a strictly limited finite string of logic gates to do it. This diagram shows how the IEEE 754 single precision standard solves this structural problem. It partitions a 32-bit block into 3 distinct operational zones: a 1-bit sign, an 8-bit exponent, and a 23-bit fraction, also called the mantissa. The 1-bit sign dictates if the number is positive or negative. The 23-bit fraction stores the core digits of the number, utilizing an implicit leading 1 to save a bit of storage space and optimize the scientific notation. The 8-bit exponent acts as a sliding radix point. It multiplies that fraction by a power of 2, allowing the hardware to represent astronomical values or microscopic decimals using the same 32 bits. To handle negative exponents without needing complicated negative number binary math, this standard uses a bias 127 system. The hardware simply subtracts 127 from the exponent's raw binary value. Not all numbers use this layout. Standard signed integers reject this 3-part structure completely. Instead, they use a format called 2's complement, which eliminates the redundant -0 problem found in earlier systems, giving hardware a single clean 0 value. These protocols establish the precise bit width of every payload, defining the exact amount of data the hardware must fetch for every operation. Looking at this abstract motherboard topology, we can see a literal spatial gap separating the central processing unit on the left from the main memory, or DRAM, on the right. They are connected by 3 parallel geometric pathways, called buses. When the CPU needs data, it asserts a specific binary location on the address bus to target the exact block in the DRAM. Simultaneously, it uses the control bus to dispatch physical synchronization signals, explicitly telling the memory to execute a read or a write. Once targeted and commanded, the DRAM pushes the requested raw electrical payload back to the CPU across the bidirectional data bus. The CPU executes instructions at blinding speeds, but DRAM is physically constructed with tiny capacitors that leak charge and must be constantly refreshed every few milliseconds, making it comparatively slow. Relying solely on the system bus to fetch data across the motherboard from DRAM creates an unacceptable latency bottleneck. The CPU would spend most of its time sitting idle, waiting for data to arrive. To keep the CPU fed, the architecture requires a physical intervention. That intervention is cache memory. Built directly into the CPU architecture using static RAM, it requires no refresh cycles, serving as a non-refreshing, hyper-fast staging ground. Cache relies on 2 primary assumptions to defeat latency. The first is temporal locality, the hardware's statistical assumption that if a piece of data is requested right now, it is highly likely to be requested again in the immediate future. The second is spatial locality, the assumption that data stored sequentially next to the target data in memory will be the next thing the CPU asks for. This spatial assumption changes how the bus pulls the payload. This visualization shows how the system doesn't just fetch a single 32-bit variable, it pulls a larger surrounding block of adjacent memory over the data bus, moving it all as one physical unit. This block is slotted directly into the L1 cache. This is the smallest, fastest tier of memory, embedded immediately next to the execution cores for instant access. If the CPU can't find what it needs in L1, it checks the L2 and L3 caches. These are larger buffer zones that catch the misses from L1, with the L3 cache often shared across multiple processor cores. The cache hierarchy turns a slow, physical retrieval process into a highly probabilistic game of anticipation. By keeping the most likely next instructions queued up, it successfully masks the physical limitations of DRAM from the CPU. With data constantly flowing in and out of the cache, the CPU faces a search problem. How does it instantly know if a specific memory block is currently housed in the cache without wasting time searching the entire space? Here, we see the set associative mapping compromise. A block of memory from DRAM is assigned to a specific set in the cache. It can occupy any available slot within that specific row, successfully balancing search speed with flexible storage. When the CPU alters a variable, it often uses a write-back policy. It writes the new value only to the L1 cache to save time, deliberately leaving the original data in the main DRAM outdated. To track this discrepancy, the hardware uses a dirty bit, a single toggle that flips to 1 to flag the cached block as altered. This signals the system that this specific block must eventually be synchronized back to DRAM. The hardware constantly manages this delicate tension between operational speed and architectural accuracy, ensuring memory consistency without crippling the processor. Executing a single line of high-level code initiates a physical chain of events that cascades across the system's logic gates. First comes the targeting phase. The CPU asserts the physical address on the address bus and fires the command over the control bus. Next is the retrieval phase. The data bus hauls a spatial locality block from DRAM across the motherboard, seeding it into the set associative cache hierarchy. Finally, the execution phase. The CPU fetches the block directly from the L1 cache, checks the dirty bit, and decodes the raw binary into a floating point number using the rigid IEEE 754 standard. Take a look at these early mainframes. The exact same buses and memory constraints we rely on today were once room-sized physical objects, highlighting the spatial separation between processing and memory. Software variables are an illusion. High-level computing only exists because of the rigorous underlying physical orchestration of buses, cache hierarchies, and rigid mathematical representation protocols.